Good morning.
Good morning.
Good morning.
Good morning.
Good morning.
Good morning, Melissa.
Good morning.
Good morning.
Good morning.
Good morning, Shaq. Mamma mia. Okay, girls. Let's see if we can get back on track of what we did the other day. Now, girls, we can mainly say that, okay, yes. This is a great intensity. It could be as okay, similar as okay, great. Power and okay, as a great amplitude. Very main, yes, okay, here I will recall is okay, a decrease in the blue ones here, right? Okay. Or we can say it's okay. Reduction of these. Oh, yes, okay, SV is okay. Later on, we say yes, okay, it's going to be yes, okay. Attenuation of. That's okay. Yes. That will mainly mean that okay, that's where we are left with is going to be yes, okay. This. In terms of intensity, power, amplitude, which means yes, okay, will mean that okay, is here we have a lower intensity, we have a lower power, and VS, okay, also as a result of that, have okay, is a lower amplitude compared to what we started with. Clear? Now this comparison, okay, the remaining can say that okay, yes, this one here is okay, maybe is okay, let's say it's okay 1,000 times. What we have over here. Clear? Which means or mean that okay, as what we have here is going to is okay 1,000 off. It's okay where we started with. Clear? Now, when you have a comparison of this, we can mainly say that's okay that as the power went from okay as a big power to a low power, it is okay reduced or is decreased or is going to it's okay be attenuated to 1,000 of the initial power or intensity or amplitude. Did that make sense? Now this 1/1000 here can mainly as okay also be as okay, sorry, written as okay as 10 raised to the power minus 3. Clear? Because okay, what the value of 10 raised to the power minus 3 is going to be is 1/1000. Clear? So what the negative sign here is okay mainly indicates is that it is understood that okay as your initial power, intensity and or amplitude decreased or reduced, or as okay as we later on will refer to is going to be as okay attenuating. How much? Mainly as okay, we can say as okay 2, where is going to be as okay the same value of 10 raised to the power minus 3. But the minus factor here is okay mainly also indicate that okay as we end up with a fraction of the initial. Fraction of what's going to be as okay mainly as okay just work. Or be as okay 10 raised to the power 3. Okay. Which will be as okay 1,000. But the negative sign may indicate that okay as it is a fraction of the initial. How big or small of a fraction? Yes, okay, it's going to yes, okay be worth or have yes, okay the intensity, which is 1,000 of what we started with. Clear? If it was, let's say it's okay, reduced by 10 raised to the power minus 4. Now that means it's okay, we just mean that okay, it reduced to 1/10,000. Clear? That the power and amplitude and intensity that we have over here is equal to 1/10,000 of what we started with. Clear? Okay. So this is mainly as okay as we will say as okay. This way here is okay. We express it as okay as 10 raised to the power any value. That is the logarithm. Or we can say is okay, logarithmic presentation of what? The relative values between yes, okay, what we started with, which in this case here is okay is going to be great comparing to yes, okay, what we end with, which in this case here is going to be yes, okay, low. So mainly because the gray is okay, our initial is greater and the final is lower. That's why it's okay. The change that happens is that okay, yes, it's going to decrease, it's going to reduce, it's going to yes, okay, attenuate. Did that make sense? Yes, girls.
Yes.
Okay, good. Whereas if we go in the opposite direction, now let's say that okay, as we went off in the opposite direction, that okay, as we started with let's say it's okay, a low power. Because it's okay, we start with a low intensity, and since that is going to is okay, be a small amplitude wave. Okay, but what mainly happens is that okay, yes, these parameters here is okay will increase. That will mainly mean that okay, as we end up with having where okay, as the power is going to yes, okay, be greater power, that will be yes, okay, a greater intensity. And that will be yes, okay, a greater amplitude. Clear? Where, oh yes, okay, in this case, when we compare this to this in a logarithmic fashion, that's because okay, what mainly happens here is that okay, yes, the power increases. You can say okay that there is okay as a gain of. You can say okay, there'll be an increase in, there'll be gain of, or there will be actually it's okay, we're gonna say it's okay. Amplification of these three bigness parameters here. Clear? But when we as okay, it's expressed that in okay as a logarithmic fashion, that is just going to be simple 10 raised to the power anything. If we said 2, that would mainly mean that there was going to be as okay an increase and gain of or amplification of the power, intensity, and amplitude 100 times. That our final power here is going to be as okay 100 times what the initial power was, or the final intensity is going to be 100 times the initial intensity. Clear? Whereas if we said 10 raised to the power 3, that means it's okay, just means that there's okay as 1,000 times increase. Did you ladies get that?
I have a question.
Huh?
I have a question.
Yeah.
So, the smaller number will still be a fraction when it goes from smaller to bigger, correct? So it still will be like if it increased
No, it
by
doesn't.
100
It doesn't necessarily have to be a fraction.
or a decimal.
No, not necessarily. You can say it's okay. Here we start off with 1 milliwatt. And you go over and say, yes, okay. $100 milliwatts. What you mean is okay, can just see here is okay that this number here is greater than this.
I got it. Okay, thank you.
Clear?
I
Okay.
have a question.
Yeah.
Sorry, so can you just confirm something for me? So if the exponent is like -4, is it negative 1/1000th or just 1/1000th?
No, it's going to be, listen, if you have a negative exponent, you say it's okay, anything. The number doesn't matter. You can say it's okay. We can say 4. But since yes, okay, the exponent here is negative. What this negative thing here actually does is that, okay, this whole thing here becomes a fraction. How big a smaller fraction? It will become, yes, okay, 1 over 10,000.
Okay, so it's not negative, it's just 1 over 10,000.
1 over 10,000.
Okay, thank you.
You write it as a negative exponent. This, like the mathematical value of these. So this is going to be equal to this, which is also, that's okay, we can say it's okay, it's going to be equal to this. Oh, sorry.
But it's always positive, right? It's just not, it's never negative. It's just always positive. Like the actual decimal and the fraction.
Well, my dear, the worth of these are all the same.
Right, okay, gotcha.
Right, okay. Okay. Whereas now we can mainly say it's okay. Practically, it's okay what these would have been positives, but they don't write the plus. So if you see as okay, 10 raised to the power 3, what would that mainly mean? That means it's okay, just mean 1,000. Clear? Whereas you say it's okay, 10 raised to the power minus 3. Now what the minus here is okay indicator, okay, as you will end up with a fraction.
Gotcha. Thank
Now
you.
this fraction here can also be written in a decimal form, right?
Yes.
This is also worth 1 of 1,000.
Okay.
Clear? Okay. So it's pretty much okay. Whereas, okay, that's all okay. Yeah. Okay. So when you say as okay that we started with okay as a smaller value, or I guess that's okay, lower power intensity and amplitude in this case here. What the amplitude, power, and intensity of our sound wave ends up with is going to be greater than what we started with. What are you going to have? That's going to be, it's okay, we can say that okay, it will be an increase in the power, amplitude, and intensity. Oh, yes, okay, this increase is okay, will later on be used, that's okay, we actually use the word gain of power, intensity, and amplitude. Or amplification of the power, amplitude, and intensity. Clear? That just tells you that, okay, yes, your final value is greater than your initial value. Did that make sense?
Yes. Thank you.
But to express how much bigger is your final compared to, it's okay, what you start with. You can say, well, okay, yes, it increased 10 times. It increased 10 times, then you immediately says, okay, that there's going to be an increase or gain of 10. That's okay, mean that's okay, that's 10 raised to the power 1, which means simply 10. So here you don't really have to write the 1. It's good enough to say, okay, that increases 10 times. You can say it's okay if it increased 100 times. This 100 times can also be written as 10 raised to the power 2. You can say it's okay, there's an increase of 1,000 times. This 1,000 can also be written as 10 raised to the power 3. 10,000 times 4. And so on. So what are the exponents here? I mean, yes, okay, that's telling you. That's just okay, how many zeros do you put after the 1? The same applies here. 4 was telling me, yes, okay, they're going to, yes, okay, be 4 zeros after the 1. But mainly because it says minus, what that minus mean, that is going to be a fraction. Did that make sense?
Yes. Thank you.
Clear? Okay. So when you say it's okay that I'm left with okay as 1,000 or 10,000 or 1,000,000 of what I started with, that's when we it's okay. You say it's okay. We started with big and it's small. That's why it's okay. Your power, intensity, and amplitude decreased. It reduced. Or as okay, as we will say later on, it will attenuate. Is that clear?
Yes.
Good. So girls, this was, we can say it's okay, the logarithmic form or version or way of expressing the, that's okay. In this chapter, we primarily going to, yes, okay, be dealing with the decrease of, okay, yes, our bigness parameters. In a later chapter, most probably, yes, okay, I think it's chapter 14, we will be dealing with in the opposite way and say increase. It's the same math. Just when something's just okay, increase, it's going to be as okay, positive logarithms, or as we'll talk about later, or today is going to be positive decimals. Whereas, okay, if something decreases, it's going to be as okay, a negative logarithm. Where you say, well, okay, I just end up with, okay, as a part or a fraction of what I started off with. Now, when I say a fraction, that doesn't necessarily mean that that has to be expressed as a fraction. You can say, okay, 1,000 watts, that's 1 watt. Clear? That final number is still not a fraction, but it is a fraction of what you started with. It's a 1,000th part of your initial. Did that make sense? Okay. Any questions? Any questions? Okay, so what we mainly, yes, okay, just do here is we compare, yes, okay, what we started with to what we end up with. And that can be anything, well, okay. Generally speaking, yes, okay, you can do that for anything. In this chapter, as okay, in ultrasound physics, it's only going to be as okay, your power, amplitude, now amplitude and intensity that we will look at. Because these are the only 3 of your 7 parameters that said, yes, okay, they are going to decrease. Okay, so primarily, yes, okay, what we're doing in this chapter is, okay, dealing a bit with that decrease. Is everybody clear about it? Okay, what 10 raised to the power minus 5 would mean? That your has decreased to, yes, okay, 100,000 of your initial. Okay. Another thing goes, if the question say that, okay, as there's a change of, and the logarithm is in a negative value, it doesn't have to say reduce. It doesn't have to say decrease. It doesn't have to say attenuate. That negative logarithm. All you can say is, okay, a logarithm with a negative value is the hint that your final power, amplitude, and intensity is lesser than the initial.
Can you explain that again? Like I heard you.
You heard me, so you should have understood it. When I say that, they say, well, okay, yes, there is a change of 10 raised to the power minus 3. What this automatically is okay should say is okay. Bring to your mind is that it attenuates, which means yes, okay, means that okay as it is reduced, or we can say it's okay decreased. Mainly because they say it's okay, there's a change of this much between yes, okay, your initial power, amplitude, and intensity, and your final power, amplitude, and intensity. It doesn't necessarily, the question doesn't necessarily need to tell you that, okay, it is reduced, or is decreased, or it has attenuated. That's something that you should figure out from this value here. Because what was I said, okay, 10 raised to the power minus 3 means? I mean, it's okay, just the minus here is that your final power, intensity, and amplitude is lesser than your initial. So don't tell me, Mike, the question doesn't say that, okay, it is reduced. Well, okay, it doesn't have to say it in the word. Because what this here will mean indicated, okay, yes, it is reduced. Or you should not be saying, Mike, the question doesn't say that, okay, yes, I don't see the word decreased. Well, okay, I do. Did that make sense?
Yes.
So if it says change of, only then, yes, okay, we'll tell us, need to tell you, like, is it a minus or plus? But usually it's okay, plus will not be written, okay? But then it could be any number as an exponent. 2, 2. But if it says reduced, then it automatically understood that, okay, yes, the final power, amplitude, and intensity that you end up with is greater than what you started off with. Clear? Okay. How much reduced? That's okay. That's going to be determined by as okay the, you can say it's okay the logarithmic value. Did that make sense? So you will see that, okay, as there are questions where it doesn't use the word reduced, attenuate, or yes, okay, decreased. Or whereas, okay, you can maybe say, okay, that the value that they have given you, or we can say, okay, the logarithmic value is the clue itself. That it means that it's okay, it's reduced. Why? Because it's in a negative form. Any questions? So when you create, okay, compare that change between initial and final in tens or times of tens, that would be logarithmic. Did you girls get that? Okay. In this chapter, we made that's okay, just going to go from big to small, or from larger values to smaller values. Because what happens is, as sound travels through the medium, power decreases, amplitude decreases, and intensity decreases. So what you end up with a final is going to be as okay, smaller than what you started with. So that'll be as okay, a logarithmic negative change. Clear? Hey, ladies. Now goes the other way in which it's okay, this comparison here can be expressed between it's okay, initial and final. And or we can say initial and final is going to be as okay in the form of what we call decibels. Now, ladies, I briefly mentioned this, yes, okay, when we talked amplitude and said, okay, amplitude, yes, okay, it has a relative unit, which would be decibels. Okay, but the golden number that we go with here is going to be as okay, 3 decibels. Now, mainly as okay, as we see here, it's okay, there's going to be as okay an increase in the power, amplitude, and intensity. Because when it says okay, that for instance, here's okay, what we have was the initial power. And initial power intensity and initial amplitude is low, and we end up with a big. Now, how that is going to just okay be expressed in terms of decibels is going to be as okay by numbers of 3. Okay, so we can say it's okay, 3 decibels, 6 decibels, and 9 decibels. Okay, now don't say who came up with the number 3 as the standard here. That's not me, and I don't know who did it. Okay, but what we made is okay, just consider yes, okay, will be a case here is that the change of 3 decibels is mainly going to mean that okay, yes, it will increase twice. Whereas we say as okay, a change of 6 decibels mainly will mean that okay, yes, it increased 4 times. Whereas, okay, as a change of 9 decibels, mainly will mean that, okay, it's an increase 8 times. Did you girls get that? And in all these here, we can mainly says, okay, what happens was that we had an increase in the intensity. We had increase in power, we have increase in amplitude. How big or small of an increase? If it's at, there's okay, a change of 3 decibels, that will mainly mean that, okay, your final power is going to be twice as much as the initial power. That the final intensity is going to be twice as much as the initial power intensity, and so on. Whereas if you say, okay, there's a change of 6 decibels, that will mainly mean that, okay, your final power or intensity or amplitude is 4 times as much as your initial. Whereas if we go at a change of 9 decibels, it increases 8 times. So you can mainly say, okay, the final values are going to be, okay, 8 times as big as your initial. But that is expressed as a change of 9 decibels. And practically speaking, as okay, since here as okay, we have an increase. We have okay, as that increase can also be referred to as a gain. That gain can also as okay be referred to as an amplification. Okay, so practically as okay, what it should have been heard, it should have been expressed as positive decibels. Clear? But that positive decibel is okay, will only be given if the choir is okay, if you asked a change of plus 3 decibels, plus 6 decibels, plus 9 decibels. Where if it said, okay, that there's an increase, if there's a gain or amplification of 3 decibel, that will mean that it doubles. 6 decibel, I mean it increases 4 times. 9 decibel, it increases 8 times. Okay, you can go as okay 1 step further and say as okay, then what about 12 decibels? Now, I mean, that's okay, just mean that okay, as there's an increase of 16 times. But the only values that you ladies will need to remember is these 3. Did you girls get that?
Yes.
Good. Whereas now, on the other hand, we said, and that's mainly as okay, what we'll be dealing with in this chapter here. Is that okay, as what did we have? Yes, okay, our initial power. That was the one that was greater. Whereas, okay, as our final power was lesser. So what mainly happens, yes, okay, here, well, we can say, okay, what is the change here? That's mainly as okay, going to mean that okay, there will be a decrease. We can say, okay, that it will be reduced. And or that's okay, as we may say, as okay, it will attenuate. Now, as that is expressed, that's okay, again, that's okay with our Favorite unit here is okay, decibels. It's again going to be okay, dB, dB, dB. And we can just say it's okay, dB. The number, ladies, is still going to is okay, be 3, 6, 9, and 12. But mainly because, okay, we say it's okay that our final intensity, power, and our amplitude is lesser than the initial because it reduced, it decreased, and oh, it's okay, it attenuated. That's how it's okay. These are going to be as okay, negative decibels. Clear? And what does -3 mean? That mainly is okay, just mean that that's okay as is a change where the initial intensity, or you can say, okay, the final intensity is going to be equal to half of the initial. And -6 decibel, we mean that, okay, yes, sorry. That there's a reduction in the power intensity and amplitude so that the final intensity is 1/4 of the initial. So like here, 1/8. And we can go and say it's okay, minus, so I mean, it's okay, it's going to be, it's okay, 1/16. But again, it's okay, as I said, the only three that you actually, you goes actually, it's okay, we'll need to remember the values of is these three here. So if you're asked that, okay, yes, there's a decrease of 3 decibels. That decreases, yes, okay, mean that, okay, yes, is negative. Or we can say, okay, the value of your decibel is in the negative, which means it will automatically mean that, okay, it's going to become a fraction. Fraction of what? Or your final is going to, yes, okay, be a fraction or a part of the initial. Clear? Okay. Whereas if says, okay, there's a change of -3 decibels or -6 decibels or -9 decibels. That's -3, -6, or -9. Meaning it's okay, automatically indicated, okay, yes, there's a decrease. There's okay, that it is okay, is reduced, and or it is going to be, it's okay, attenuated. Which means okay, what you are left off with is as respective fractions of the initials. Okay. Where you can mean it says, okay, when it goes like this, the final power is half of the initial. The final power is 1/4 of the initial. The final power is 1/8 of the initial, and so applies for your amplitude and intensity as well. So again, go, yes, okay, what is that you see here? That the negative sign mainly is okay, just made them fractions, which has, okay, as where the number here compared to, yes, okay, the numbers here. Have the same, yes, okay, worth. And this is the same as this. This is the same as this. This is the same as this. Okay. So this is all mainly, yes, okay, just talking about, yes, okay, comparison. Or relative, yes, okay, measurements between your initial versus final. What you start with compared to, yes, okay, what you end up with. When you compare those values, and okay, yes, the final value is greater than your initial, you say, oh, we gained. Each value increased. Right? And then you may say, yes, okay, how much of an increase? Well, I bought it for $100, now it's worth 10,000. So it increased 100 times. Or its value doubled? Well, okay, yes, 3 decibels. Whereas if you go in the other direction, let's say it's okay, that God forbid it's okay, the house prices started again. You might buy a house for 3 million. And now it's only worth 1 million. What happened? Well, okay, yes. If you sell it today, yes, okay, you're going to, yes, okay, lose 2 million. Or you can say, okay, I'm going to lose 2/3 of what I paid for it, right? I'm only going to receive 1/3 of what I paid for it because you paid 3 million and now it's just being sold for just 1 million. So you can do that with pretty much okay anything. But when the final number is greater than the initial number, that will be a gain. Then, okay, if it's opposite, it will be a loss. Did that make sense?
Yeah,
Anybody do shares? Have anybody invested money in shares?
yeah.
No.
Why you skin up your face? Why you make that face?
Okay. I don't know why I'm making that face. That's just my face. Yeah, but you have to be on top of those things. Not everybody who knows how that works. So unless you don't, that's okay. Know how, that's okay. Shares and stock market works, and that's okay. Also following trends and so on. So you may be looking for, as okay, a grade attenuation, a grade reduction. Or you can say it's okay, loss. But is it really how that works? No goes. There's a lot of insider jobs in the stock market. Like for some time, it's okay. I think people were as okay into buying Bitcoins, right? What do they call those cryptocurrencies? And I say, well, okay, as you probably have a lot of money that you never physically see because Theoretically, yes, okay, it's out there somewhere. Who got control of it? Who is actually handling it for you? You have no effing idea. And if you just hand money to somebody, you never know, yes, okay, what's going to happen. The time he or she realizes, okay, it's not worth it to, yes, okay, disappear from the surface of the earth. They disappear. And yes, okay, you are left with, forget about it, okay, you're left with zero. So, okay. But here, yes, okay, it's all, yes, okay, relative. What did we start with? To come, yes, okay, what did we end with? So the easiest way to sort of understand it is, if your final number or value of anything is more than, yes, okay, the initial, you had a gain. It increased. Clear? That can be, as okay, expressed as positive logs, that can be expressed as positive decimals. Whereas, okay, if it's in the opposite direction, that your final value is, okay, what you end up with is lesser than what you started with, you lost. Okay. And that will mean, yes, okay, when you compare those two, yes, okay, that's going to be, yes, okay, expressed as negative logs, negative decimals. Clear? When we go in decibels, it says, okay, 3 and -3 is respectively double and half. 6 and -6 is respectively 4 times and 1/4. Nine decibels is respectively, or because that's okay, 9 and -9 decibels is respectively 8 times and 1/8, or 1/8. Did you girls get that?
Yes.
So that's how we relate, yes, okay, our initial value to, yes, okay, the final value. Did it gain, did it loss? The next thing is, okay, how much gain if it gained? How much loss if it lost? That how much can be expressed in two ways. Logarithms, which is going to be, yes, okay, in tenths. And decibels, where we have this weird formula, 3, 6, and 9, -3, -6, -9. It goes on. But mainly, yes, okay, we stop with 9, mainly because I told you guys, okay, those will be the 3 only values that you'll need to remember. Is that clear? Okay. And one of these values here that you have to, yes, okay, make sure that you need, oh, yes, okay, remember is worth off. It's going to be this one here. And why? You will see that later. Now goes on page 79, are there a list of 10 questions? Do them all and I will see you goes at 10:15. So get your coffee, tea, whatever. And see if you can answer these questions here. Capiche? Yes, girls. Welcome back. Did you girls try to answer the questions?
Yes.
Good.
Yeah.
Any issues? Any question that was giving you a hard time?
Yeah, question 5, when we're talking about the negative 10 decibel,
Mm-hmm.
we didn't go over 10, we only did 3, 6, 9. Or should we know
That's
10?
how we know it's
Minus
110.
10. That no, you when you see
Okay, so I
10,
take out the button.
it's a logarithm.
Okay,
Sir, can
Yeah,
you?
so if it goes by tens, it's a logarithm. That's why I say it's okay. Tens are logarithms. Okay.
okay,
Yeah. Okay. So minus 10 means okay. 10 raised to the power minus 1.
okay,
Clear?
Yeah.
Did that make sense?
yes, it did.
In number 8,
Hmm. Okay. Just look here. Now, what does 8 read out as? A wave's intensity is 2 milliwatts per centimeter. So we can say, okay, the intensity is 2 milliwatts per centimeter square. Now comes the thing. There is a change of plus 9 decibels. Now, my dear, when you see, okay, change. Now, change here can mean as, okay, either increase or decrease. Yeah. So since the word change is an unspecific term, because it can mean both increase or decrease. That is why it's okay. They say, okay, so what change do we have? Well, okay, it's a positive number expressed in decibels. Now, the next thing is that says, okay, now what you mean is I need to know is, okay, what is the change of plus, sorry, plus, which means is, okay, will be an increase. So what was the worth of 9 decibels? That it increases 8 times. What is the final intensity? So that's straightforward. Very meaning you can say it's okay that this value that we have been given here is okay of intensity. That's going to be it's okay the initial intensity. So it means it's okay. That's going to be it's okay your initial intensity. Increase. Why increase? Because it's a change of plus 9 decibels, which worth is 8. And this is asking, okay, what is your final intensity? So that's going to become your final intensity, which will be, as okay, 16 milliwatts per centimeter square.
I think that's where I got confused at. Thank you.
Clear? So girls, they only as okay gave you as okay the exact change here, because okay, the word change can either be positive or it can be negative. Or because it's okay, it can mean increase or decrease. They had it said, yes, okay, a change of minus 9 decibel, that minus 9 decibel will mainly mean that, okay, as your final intensity will be 1/8 of the initial. For me, it's okay, we just come down to the same. It's okay that you multiply 2 by 1/8.
Sir, can you explain 9 and 10 since, it's kind of like the opposite of each other?
Why is 9 and 10 the opposite of each other?
Because one it says if the final intensity and then it increase and
Yeah,
then the 10 is saying the initial intensity and it also says it increase. So can you just explain that?
which question are you talking about here?
9 and 10. It says positive and positive.
Okay. But did you girls get that? Okay, so had it said minus 9 decibel, then okay, as you come in, it says, okay, your final intensity would have been 2 or 8 watts or milliwatts per centimeter square, which means okay becomes 1/4 milliwatt per centimeter square, which could also mean it's okay 0.25 milliwatts per centimeter square. And it says, okay, a change of minus 9 decibels. Question 9 and 10. Well, what have we been doing now? The final intensity of a sound beam is more than the initial intensity. Final intensity of a sound beam is more than the initial intensity. Right, okay, Reagan says, okay, if this is your initial intensity, this is your final intensity. So the change here is going to be as okay, what happened? We gained. Or we can say it's okay, it increased. And whenever it's okay, something is gained or increased, it's okay, your decibels is going to be positive. Now, another question we say is okay. Let's see what question 10 says. So this was your question 9. What does question 10 read? The initial intensity of a sound is less than the final intensity. So it's the same. Your initial intensity. That is less than the final intensity. Then the gain in decibels is positive or negative. It is still positive because your intensity increased. So when your intensity increases, it's going to be okay that we start with small and end up with big. So the only thing that they switch around is, okay, they start off saying, that's okay, the final intensity in question 9. And question 10, they go, yes, okay, initial intensity. Here it says, okay, final intensity is greater than your initial intensity. Here it says your initial intensity is lesser than your final intensity. It means the same. Or it comes out to the same. So that's why I say it's okay when your final value is greater than your initial, which on the other hand will mean the same as saying it's okay, your initial is lesser than the final. It's just a different way of wording the same thing. It's okay, your decibel value is always going to be positive, as we saw in the question above. You started with 2 milliwatts per centimeter square, you end up with 16 milliwatts per centimeter square. So you had a greater intensity, right? Or we ended up with a greater intensity. So question 9 and 10 means the same, just worded in a different way. Did that make sense?
Yes.
I can say that's okay. That Shanna score in the quiz was greater than your score, or your score in the quiz was less than Tatiana's. It's the same. In one case, I say, okay, just okay, I say start with Tatiana's scores comparing it to yours, and says, okay, other way, your score compared to hers. Yeah.
This is not about the questions, but when you're done, can I ask you a question on page 79, 78? The examples?
You can ask them now. Why later?
Okay, no, because I didn't want to interrupt you.
Go ahead.
When it says therefore the decimal notions used for 100 is plus 10 dBs and another plus 10 dBs, that equals plus 20. How can you explain that? That when I'm looking at the example and I
Look, dear. Now, my idea is, okay, mainly because it is a comparative unit, a relative between initial and final. Or we can say it's okay, initial and final. Clear? It is always going to, yes, okay, be expressed as decibels. So this decibel here is okay, is mean that's okay, just the relation between this to this, or this to this. Okay, now if the number here is, so actually it's okay, a multiple of 10. Then it's okay, we'll go, it's okay with the logarithm form. So yes, okay, it's 10 multiplied by 10. Actually, it's okay, we mean this. Or can also, it's okay, be expressed as this.
Okay, I got that part.
Whereas in the other one, the main is okay, just go, then your main is okay, we'll say, is the decibel value a multiple of 3? Oh, sorry. And we'll go 15 and 18 and so on. Where this will mean this. This will mean this. This will mean this. Did that make sense?
Yes. Any questions? So mainly that's okay, because that's okay, just two things you will need at least need two things to determine, yes, okay, you can say it's okay, changes in your intensities or power or amplitude. Clear? They may give you, yes, okay, a final power and say, okay, this is the power that you got after, yes, okay, change this much. Where that change can be expressed in terms of logarithm or decibels. What is the initial power? Clear? They can't go the other way around and say, yes, okay, this is your initial power. It undergoes this much change. And they will ask you to calculate out the final power. Just as we had in question number 5, I think, right? No, 8, sorry. Right? Then they may say, well, okay, this is your initial power. And this is your final power. How much change did it undergo? Which can be either as okay in terms of such okay, decibels, the 3 formula, or log. Did that make sense? Any questions? So you will leave these as okay, 2 values to calculate the third.
right? Okay, I can't say as okay, your final power is 16 watts. What is the initial power? You say, well, okay, I need to know as okay, how much change there was between the initial and the final to determine as okay, what the initial power was. And or vice versa. So in question 8, yes, no, sorry, 8. Yeah, 8. You are given, yes, okay, an initial power. And then they tell you, okay, this is the change that occurs in it. How much does it change? What was your initial final power then? Although it's okay, they didn't say that this is the initial power. They mean it's okay, but you should be able to figure out that because they ask for the final power, intensity, sorry. Did you girls get that? Okay. Any last question?
I have one more question.
Mhm. Go ahead.
So the change in, I'm still on 78, the change of plus 20 dB.
Mhm.
How is 10 dB and another 10 dB equals 20? And how is that 20 equals 100?
Because, okay, listen here. They mainly is okay, just says okay that this 10 dB, just like we had, it's okay, you can say it's okay. We can say it's okay, 3 dBs means double. So where you mainly can say it's okay, you know, where did we get this here from? Okay, now this means it's okay, or mean it's okay. We can say it's okay. 10 plus 10, right? Okay, but what it actually is okay is this actually is okay, it's from is okay, your exponent of 10. And this means 100.
Okay, now I get it. Thank you.
Clear? Okay. Where then you can say as okay, 30 to be mainly as okay would be as okay, 10 plus 10 plus 10. Okay. Or you can say as okay, your main had been as okay, 10 raised to power 3, where it becomes 1,000 times.
Got it. Thank you.
Okay. Okay, girls. Now let's see if we can start off with, okay, yes. One of the major topics of this chapter here. And okay, probably that's okay, a topic that we're going to just okay be sticking with for us okay quite some time as we just okay go through this chapter here. Now, what I said the other day was that okay, yes, we had a transducer. And this transducer has okay, what it produced was just okay, we can say okay, sound waves, which we say is okay, had a initial amplitude, power, and intensity. Okay. Now, as this sound wave here is going to, it's okay, cross, or you can say it's okay, get in contact with different tissues. What is going to happen is that, okay, as a part of the energy that this initial sound wave here carried in form of power, which was going to be related to its intensity, which was going to be related to its amplitude. Part of that energy is going to just, okay, get reflected back. Which mainly will mean that, okay, as at this point here is okay, or between is okay, these two neck tissues here, you will have a lower power or lower intensity or lower amplitude. And okay, when this comes across us against again the next tissue, some of the energy that, okay, as this sound wave here will be carrying, some of that energy is going to just, okay, get reflected back, which mainly will mean that, okay, yes, what we have continuing here is going to be as okay with a lesser amplitude and intensity and power. Which, okay, when it hits this other tissue, is okay, some of the energy that it carried is going to just, okay, get reflected back, which may no cause that, okay, as it proceed, there will be a lesser amount of energy. Some of that energy is going to just, okay, get reflected back. And we can mainly say, okay, at this point here is okay, it's a very low energy. Whatever is okay, some of that energy we can reflect it back. But what we mainly saw here, what we mainly said here was that, okay, yes, as this initial sound wave here travels, what is going to happen? Its power, its intensity, and its amplitude is going to just, okay, decrease, 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 as it travels deeper and deeper and deeper and deeper. And what actually is, okay, caused this decrease here is mainly as, okay, because the sound is being, you can say, okay, these three bigness parameters here are being affected by the tissues, which cause these as, okay, three parameters here to decrease. Clear? Had it not been for the media, had there been no media in the middle, this sound wave here is, okay, or mainly as, okay, just had traveled with no change theoretically. Clear? Did that make sense? Then there was, okay, you guys said, okay, there had been no decrease in the power, no decrease in the intensity, no decrease in the amplitude. But mainly because, okay, it came in contact with different medias at different depths. Each of these media here was going to, as okay, each of these tissues here are going to have, as okay, their own effect upon the Okay, we can say, okay, determine how much energy is going to, yes, okay, be sent back to the transducer. Which we mean, yes, okay, roughly can say, well, okay, yes, the remaining amount of energy is going to, yes, okay, just carry on. Did that make sense? But mainly because that's okay, different tissues, different amount of energies are going to just okay be sent back to the transducer. But and we mainly says okay when we compare the intensity or the power of our initial wave to just okay as we said earlier, the power and intensity of the final wave here. This one here had decreased. And that decrease or that reduction, or as okay, that attenuation of the wave mainly meant that okay, as our initial power, or initial intensity, or initial amplitude was greater compared to yes, okay, the final power, the final intensity, and the final amplitude. Because it decreased, it reduced. Or yes, okay, the sound wave attenuated. Did that make sense? So please, 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 comparing, yes, okay, this initial here to the final. Where we mean, yes, okay, say that, okay, as the initial is greater than the final. That change only applies to the power, intensity, and amplitude. Which only mean that okay, it's only going to be as okay, these three bigness parameters or three bigness parameters that are going to undergo that decrease as it travels through the tissues. Clear? Did that make sense?
Yeah.
Which mainly will mean that, okay, yes, things such as, okay, as your frequency remains unchanged. Things such as, okay, as you can say, it's okay, your period remains unchanged. Clear? Because that's okay, the wavelength. Or okay, we can say the wavelength here to here, here to here, here to here, and so on, so on, so on. Okay, well, yes, okay, go up and down or fluctuate. You may have a greater wavelength here and an even greater wavelength here, and then yes, okay, here is okay, the smallest of all wavelengths, which okay, as maybe as okay, lesser here. Okay, where you can mean says okay, it is not a constant decrease of the wavelength as it travels through it, okay, and comes in contact with different medias. Likewise, okay, the speed. That means it's also going to okay be determined by okay the different medias. So it can be as okay, the speed can be high here, then it can be very low here. Something like that, right? Okay. So it's not going to be as okay a constant decrease. That constant decrease as the sound wave travels through media, mainly as okay, only happens for power, amplitude, and intensity. And that constant decrease is what we will call attenuation. Which mean that okay, as your initial power is always going to be greater than the final power because the power attenuates as it travels through the medium. The same applies for your attenuation intensity, mainly because okay, your initial or your intensity is always going to attenuate as it travels through media. And so for your amplitude. Where you can mean that okay, in this case, okay, the initial is always going to be greater, and your final is always going to be less. You might have started here with okay, let's say it's okay, 100 watts. Okay. But here you may as okay, just be left with okay as 1 watt. Did that make sense?
Yeah,
So as sound travels through the media, or it's okay, in this case, it's okay, tissues. The things that are going to constantly decrease is the power, intensity, and amplitude. And that decrease in the power, intensity, and amplitude is what we will call attenuation. So please keep in mind, girls, attenuation is the decrease in power, intensity, and amplitude. Where we then can say as okay. How mainly as okay, we can say as okay, as a result of its as okay contact or as okay interaction with medium. But what we mainly can say is okay that this attenuation here will mean attenuation of power, intensity, and amplitude is that our initial PIA always is going to be as okay greater than as okay the final PIA. Which should be less. Or it can also be worded as delta final PIA is going to be lesser than the initial PI. If we can say it's okay here, this was great. This was less. Which may mean, okay, this is going to be less, and then this one here will be great. But these two sign here, okay, this sign here is okay, meaning just reads as is greater than. And this one sign here means okay, just reads as is lesser than. Or yes, okay. Somebody is okay, give my a cheat back in the days. And we say, okay, the sign is like this. And then you say, well, okay, that's right. Yes. If not, just think of this thing as okay, being as okay, the mouth of a shark or crocodile. Which always is okay, is open towards the greater. Because this shark or crocodile here is okay. If we see as okay, a big piece of meat versus a small piece of meat, it will go for the big one. If we see as okay, a small piece of meat versus a big piece of meat, it will go for the big one. Okay, girls. But when we say that a sound wave attenuates, all that's going to be as okay, change of negative decibels or negative log. That may mean that okay, as the initial is greater than the final. Okay. And what parameters are we talking about, girls? Only your three bigness parameters will decrease. Okay. That was written in chapter 3. At that time, I told you that, okay, that decrease, that is what we call attenuation. Here we is, okay, does repeat that very same thing here, but now as a separate topic. Did you girls get that?
Yeah.
Right? Then we said, well, okay, we used the example and said, well, okay, let's say it's okay, me standing in the parking lot, talking to you, it's okay, some of you girls. You'll be able to clearly hear what I'm saying, hopefully. Compared to as okay, somebody standing in the gas station may not be able to hear me so clearly. Not to talk about as okay, somebody standing by the Dunkin' Donuts, which is further down the street. Not to talk about as okay, somebody standing all the way by as okay, the highway. Because what is it that my sound is going to do as it travels that greater distance? It will attenuate more. So the people who are standing right next to me, yes, okay, may be able to, yes, okay, clearly hear what I'm saying. Unless, yes, okay, right? Okay, if I'm whispering that, I may be the only one who knows what is being said, mainly because, okay, it's me saying it. Did that make sense? But then we can say, it's okay, the more I raise my voice, well, okay, the more deafening it's going to be for you girls. But we can also say, as okay, we'll be able to, as okay, travel or be as okay, able to be heard for a longer and greater distance. Did you girls get that? So if the intensity increases, if the core power increases, which may not cause us, okay, the amplitude of the wave is going to increase. That will be able to just, okay, travel a greater distance before it attenuates to the same level as a power, as a sound with a weaker power or weaker amplitude or weaker intensity will be able to travel. Did you girls get that? Okay. Now, the next thing that your book talks about is mainly, and please girls, you gotta be careful with these words here, because you will be fooled into, yes, okay, answer the wrong answer. And some of you might already have seen, yes, okay, how that works on the quiz that we had the other day. So mainly goal, that's okay, what we have is that is going to be as okay, two factors to determine attenuation. What did we say attenuation was? Decrease in power, intensity, and amplitude, right? Yeah. This decrease here is okay, is going to be as okay, we can say okay, negative log and or negative decibel. But the two factors that determine how much a sound is going to attenuate. Those two factors are mainly going to be as okay. One is going to be as okay, what we can call path length. And this one here is simply to explain. Other factor is going to be as okay, a little bit more complex. And that's going to be as okay, the frequency. Now, ladies, let us just look at, okay, as what is it that we mean by the term path length? Now, if you look at the word length here, we can mainly say, okay, is going to be as okay, something that is going to as okay, be equal to or measured as in terms of distance. Yeah. Now, if you look at the word path, oh, shit. You say it's okay, I took this path here. I may have taken as okay the same path, but then it's okay, I just walk for a greater distance. So path length is mainly as okay, just the distance of the path that the sound wave traveled. So that's going to be as okay, one of the factors that will determine your how much is okay the sound attenuates. How much is okay power, amplitude, and intensity is okay will decrease. Now I already gave you guys that example and say, well, okay, since I'm talking, those of you who were standing right next to me could clearly hear what was being said. Why? Because there is a shorter path length. Okay, the sound had traveled a shorter distance. So it actually hadn't attenuated to the degree that, okay, as the words that I uttered were inaudible. Where we can say as okay as the sound that I produced travel a greater distance. What will happen? We have a greater path length. What was going to be the effect on the sound after that greater distance traveled? It will attenuate more. So yes, okay, it was not going to be that clearly heard, audible. Or we can mainly say, okay, why? Mainly because it's okay, its intensity decreased, its power has decreased, and the amplitude of the wave have decreased. Which mainly is okay, just brings that is okay on to yes, okay, where is the relationship between attenuation, which means decrease in the power, amplitude, and intensity of a sound wave, and the distance that it has traveled. They are going to be directly proportional to one another. So we can mainly say as okay that path length, which mainly is okay, just as a fancy word for saying as okay, the distance traveled by the sound wave. That is going to, yes, okay, be directly proportional to attenuation. Which mainly will mean that the greater the distance a sound wave has traveled, greater will be the decrease in the bigness parameter, or we can say, okay, greater will be the attenuation. And or vice versa. Maybe we could say as okay, the shorter the path length, which may mean sound has traveled for a shorter distance. Well, okay, yes, it really has it's okay, well, lesser attenuation because it's okay, a lesser decrease. Right. So if you take a sound wave that for instance, okay, I travel, that's okay, a shorter distance, let's say it's okay, 2 centimeters. It might just have it's okay, reduced to, let's say it's okay, 1/10 of the initial. Whereas, okay, it being the same wave with same initial intensity and so on, so on, so we had traveled as okay a greater distance, let's say as okay 8 centimeters, for instance. It might have as okay attenuated down to as okay 1,000 of its initial. Did that make sense? So you can say, okay, the greater distance that's okay a sound wave has traveled, the more is it that it will attenuate. Or yes, okay, the lesser distance or the lesser pathway that a sound wave has traveled, or okay, has less amount of attenuation. Did that make sense? So that's okay, the golden star here is, where is the relationship between path length and attenuation? Any questions? So mainly as okay, you can say as okay as the distance between the source, and you can say it's okay different recipients of sound increases. That can be expressed as okay as the path length increased. So those of you who are standing right next to me as okay will be able to clearly hear what I'm saying, because the sound hasn't attenuated. As the distance between me and okay as another person and another person, another person, the further yes okay that the greater that distance increases, the more is it that the sound yes okay that I produced will attenuate before it reaches him or her, his or her ears. And at some point, as okay, they will say, well, okay, Mike, we can't hear what you are saying. No, I can start as okay, screaming at the top of my lungs. Okay. Or as we did the other day, it's okay. Use a microphone or loudspeaker, right? Did that make sense? Okay. But it's okay, ear really is okay, the most powerful, yes, okay, sound system. Somebody is okay, beyond, yes, okay, a certain distance, so they would say, well, okay, we can't hear what the, because that pattern is mainly, yes, okay, just too much for that sound wave. So pattern is mainly as okay, just a fancy word that says okay, the distance that the sound has traveled. The more distance a sound travels, the more is it that it will attenuate. In our case, yes, okay, an ultrasound. Why? Because okay, as it travels, it is going to just okay come across different medias. tissues, which, yes, okay, I mean, yes, okay, said it that those tissues are going to, yes, okay, reflect some of the energy carried by the sound wave towards it, send that back. So the amount of energy that proceeds is going to be lesser, become lesser and lesser and lesser. Just put it this way, girls. Okay. Now, as far as your tissues are concerned, or media is concerned, it's not going to be as okay the same amount of energy that is going to be reflected off at each tissue. Okay. But let's say it's okay, you start your day with it's okay, $200. You go out. Now, in the first shop, you use $2. Then you go to another shop, which is further down the street. You use, let's say, $20. Then you go further down the street. Use another, yes, okay, what's that amount? Well, you can mean says, okay, you started your journey from the house and travel, go walk down the street and walk into each shop because, okay, you need something in every shop on the way. But you can mean says, okay, by the end of the street, what is that you have done? You have traveled a longer distance. And you had, okay, on the way, as okay, from point A to point B, as okay, gone into different shops, use different amount of money. And what is it that you're left with? Maybe just 20 cents. Okay, so that decrease in the amount of money from, yes, okay, $200 to 20 cents. And now it'll be expressed as, okay, as a decrease, a negative log or a negative decibels. Yes, okay, what caused the decrease was, okay, the distance that you traveled. Had you traveled half that distance, you might have been, yes, okay, left, still had, okay, $100 in your pocket. You can say, well, okay, I started with $200, I'm just left with $100, okay, that's half. The amount of money in my purse or wallet or credit card or whatever is half of what I started with. But if you choose just, okay, continue your journey, yes, okay, it's going to come, yes, okay, and to a point, yes, okay, where you may not even have, yes, okay, the money to pay for the bus back home. Because I can't carry all this as hit that I bought. Yeah. Okay. So longer distance the sound wave travels, that's okay. The more is it that it will attenuate, which mainly means decrease. And which factor will decrease? Power, amplitude, and intensity. So frequency is not going to be changed by attenuation. Wavelength is not going to, as okay, change as a result of attenuation. So is period. And so is speed not going to, as okay, change as a result of attenuation. Did you girls get that?
Yes.
Good. Now goes the next factor. And that is your frequency. And goes here as okay, when we say frequency, as okay, just to as okay, make it more specific. What we mainly are talking about is going to be as okay, the frequency of the transducer. Okay, now since we as okay say that that's going to be as okay a factor that determines your attenuation. There's going to be as okay a relationship between frequency and attenuation. Now let's not say. Yeah, okay, good. And goals for now, just remember this one here. That okay, yes, your frequency of the transducer is going to be as okay also directly proportional to the attenuation. Now, please do not confuse that with saying, well, okay, does that mean that, okay, the frequency is going to change as it travels through or decrease as it travels through the medium? No. By saying that frequency of the transducer is directly proportional to attenuation will mainly mean that the greater the frequency of a transducer, the more is it that, okay, as that sound will attenuate as it travels through medium. Did that make sense? That you will have a greater attenuation of the sound as it travels. Whereas, okay, as on the opposite side, we can say, as okay, a lower frequency transducer, a lower frequency of sound is going to, as okay, undergo lesser attenuation. The attenuation is okay, mainly as okay, still means decrease in your bigness parameters. Where you say it's okay, less attenuation is going to be it's okay, a less decrease in power, amplitude, and intensity. Which is mainly as okay, what we will see with as okay, low frequency transducers. Where okay, a high frequency transducer will cause a great attenuation of the sound, or we can say okay, which may mean that there's going to be okay, a great decrease in the power, amplitude, and attenuation. And goes, if you guys remember, we said that okay, as our max frequency was 15 megahertz. Clear? Okay, as far as okay, ultrasound was concerned. They say, well, okay, as we can only use as okay transducers with frequency of just okay 15 megahertz. Mainly because we says okay, if we went beyond 15 megahertz, if we says okay, we took a transducer which for instance okay, might had a frequency of 20 megahertz. That will mainly cause that the sound wave as okay is going to have so much attenuation that it actually is okay will not be able to as okay have any path length at all. Or we can mainly as okay say that okay it dies or attenuates even before it's okay entering the patient's body. So that's why it says okay, good is good, but then too much good is bad. Right? Does that make sense? Well, that's when they say, oh, that was probably as okay, too much of a high frequency. That high frequency has its plus points too. Okay, which was good. But then too much good becomes bad. Did you girls get that? Okay,
Yes.
so the too much good being bad as far as the frequency of your transducers is concerned is that, okay, as too high of a frequency is going to cause too much attenuation. Too much attenuation is going to mean that, okay, as the sound that I produce dies immediately. And if the sound dies, even as okay, dies off. Even before as okay, entering the patient. What's going to happen? You're not going to be able to get an image. Okay. Did that make sense? So that mainly is okay. Brings us to yes, okay, now we can make yes, okay, just take an example of how yes, okay, for instance. Now we can say, okay, we said that frequency yes, okay, was directly proportional to attenuation, right? Which mainly mean that, okay, yes, if this here one increases, this one increases. And vice versa, yes, okay. If this decreased, then this decreased. Clear? But we can mainly say, okay, now if you find says, okay, had let's say it's okay, 15 megahertz transducer. Versus let's say it's okay, 5 megahertz transducer. Clear? Now mainly because as okay, there's going to be as okay, greater attenuation is okay for the 15 megahertz transducer. It may as okay attenuate at a shorter path length. You can say it's okay. For instance, okay, at a depth of 1 centimeter. Yeah, okay, now let me just, I need to write something here as well. Just a little bit. Because it's okay, that lower frequency we said, okay, as was 5 megahertz. Now, mainly because of, okay, at the lower frequency, I mean, that's okay, mean that, okay, as it will attenuate at a deeper depth. Now, please keep in mind, yes, okay, that is the same tissues in both cases. And that, okay, your initial power, intensity, and amplitude for both cases here is the same. Clear? Okay. Which mainly we can say is okay, that will be as okay. You can say, for example, at a depth of, let's just say it's okay, 5 centimeters. So what that mainly causes is that we can mainly say, okay, that frequency actually is going to just, okay, be inversely proportional to penetration of sound waves. of sound. Okay, here it's okay, this penetration actually is okay, may also be as okay, the same as your pad depth or pad length. Where we said, okay, as we had a great frequency transducer. Sorry. That was going to, yes, okay, have a short penetration or lower penetration, which you see here. And or we had, okay, yes, a low frequency transducer, which was going to, yes, okay, then have, okay, it's a greater path length, or greater penetration. Of sound. Okay. So keep that in mind, goes that, okay, yes, greater frequency transducers have a shorter or has a lesser penetration. Whereas low frequency transducers have a greater penetration. Because the greater frequency, the greater attenuation, and the sound will die at a shorter distance. Whereas, okay, on the other hand, you say it's okay, a low frequency transducer will have a lesser attenuation, which means it's okay, called enable that sound to travel a greater distance before it attenuates. Now, please keep in mind here, okay, that's provided, okay, the initial powers for both the high and low frequency intensity, frequency transducers is the same. And that they are scanning as, okay, the same tissues. Clear? But two factors, the two factors that determines your attenuation is the path length and the frequency. And what are their relationships to attenuation? They are both going to be directly related. Which mainly mean the greater the distance, the more attenuation is it that a sound will undergo. Lesser path length or lesser distance, less attenuation. Then you go frequency is also going to be as okay, a factor that determines your frequency attenuation. So what's the relationship between frequency and attenuation? That as well is also going to be as okay, directly related. Where you may use as okay, a high frequency transducer. Or we can say that a sound produced by a high frequency transducer is going to undergo more attenuation compared to a low frequency transducer is going to undergo less attenuation. And mainly because a higher frequency transducer undergoes the sound produced by that high frequency transducer undergoes more attenuation, it will only be able to travel a shorter distance before it attenuates. And vice versa. Did that make sense? And that's where they say, well, okay, 15 megahertz, that's the maximum. Because, okay, if we go beyond that, well, okay, the sound is going to attenuate. Well, probably not, but it's okay at a crazy shallow depth, which means it's okay, make this transducer here, it's okay, you can say it's okay, unutilizable. Right, okay. If the words that I speak finishes right here, as they leave my lips, what's going to happen then? Well, okay, there was no point of having this class here, right? Okay. I could just send you guys an email and say, it's okay, read the book and see you in 3 weeks for the next test. Did that make sense? So frequency goals is directly proportional to attenuation. Any questions? So these were factors. Okay. But the frequency still remains constant. As okay, it was 20 megahertz of 10 megahertz at the transducer. You look at the frequency at a depth of, let's say, it's okay, 5 centimeters, is still going to be 10 megahertz. That frequency will not change. But it's okay, will the power be different? Will the intensity be different? Will the amplitude be different? Yes. So you can mean it says, okay, at that depth of 5 centimeters, that's okay, because it's okay, 10 was a high frequency, that's okay, that's going to be a greater difference between the initial and final power and amplitude compared, okay. They're comparing that to, it's okay, the change or the difference in the power and amplitude of a 2 megahertz transducer at a depth of 5 centimeters. Because as a result of, okay, at that low frequency, as okay, those powers, amplitude, and intensities attenuated less. Did that make sense? So two girls, yes, okay, may start with the same amount of money. But one of you is going to be as okay, a high frequency transducer. One of you is going to be as okay, a low frequency transducer. You may start off with the same amount of money, $2,000. But those of you who is a high frequency transducer, okay, every shop that you go into, you may use as okay 10 times as much money as the other girl who is a low frequency transducer. So what happens? After walking, yes, okay, half a mile, entering is okay. 10 shops. The girl who has only been spending is okay. 1/10 the amount compared to is okay, the girl who spent more will have more money left than the girl who has okay spend more in each shop. Did that make sense? So when you then compare, is okay, the balance one says, okay, I got $200 left, and the other will say, okay, well, I got only $2 or $20 left or something like that. Or I still have $200. Whereas one is just left with $2. They both started with the same amount, $2,000. They both went into the same shops, but one used more money. Right? Okay. Which may require, okay, from shop to shop to shop, yes, okay, the amount of money that she had or walked away with was going to be less compared to the one who didn't use that much. See, I don't need 3 pairs of shoes. I'm good with just 1 pair. Any questions? Good. Any questions about the relationships? You guys good? Okay. Now just take your lunch break. And ladies, when we come back, we will talk about, yes, okay, the processes. Okay, we may not get through all of them, but let's see. So I will see you ladies back no later than 12:30. And this is your lunch break. You don't get an ED day. Okay? So get your lunch done and okay, yes. See you then. Welcome back, girls. So any questions so far? Okay, ladies, so pattern and frequency, they were factors of attenuation. Okay. Which mainly is okay, just brings us okay as to the next thing related to attenuation, which is going to be as okay the processes. And we can mean as okay, the obvious okay processes that contribute to attenuation. Where main is okay when we say it's okay, when we say something is a process, that means it's okay, what I mean. Okay, when it says okay, what happens to the sound wave that causes it to attenuate. Okay. So as far as the processes are concerned, yes, okay, we have three major processes. That means yes, okay, will cause the sound wave to attenuate. Clear? And please keep in mind, go that okay, it's all these three processes here. That's okay, because that's okay. These processes here is okay, will occur at what the book mainly is okay referred to as okay as boundary, which may mean is okay. In this case, I will call it okay the tissue. Is that clear? And that's why we says, okay, this whole chapter here was about, it's okay, what happens to sound as it, okay, as interacts with tissues. Now goes the three processes is going to be as okay, what we'll call, oh, let me just write that in capital. Reflection. Other one is going to be as okay, what we can call as okay, backscatter. Or we can say okay, backscattering. And the last one here is going to be absorption. So three things that may happen to a sound wave as it hits a boundary, which are going to be processes that, okay, as you can see as, okay, that sound wave may reflect. Another thing that can happen to is, okay, to the sound wave when it hits a boundary is that, okay, as it is going to just, okay, backscatter. No, not scatter. Not backscatter, sorry. Just scattering, sorry, girls. Just scattering. And another thing, another process that can happen to the sound wave that hits a boundary or a tissue. And we can mainly say, okay, since that's okay, the sound is okay, it travels through this tissue here, is that some of the energy carried by the sound wave is going to just okay get absorbed by the tissue. But what all these three processes here had in common was that, okay, as the energy at this side of the boundary, the energy that proceeds at this side of the boundary, and energy that proceeds at this side of the boundary here is going to just, okay, be lower in power, intensity, and amplitude compared to just, okay, the energy over here, which was going to be a greater power, greater amplitude, and greater intensity. Which may cause that, okay, had it not been for us, okay, one or two or all of three of these processes, okay, the sound wave would not have attenuated as it came in contact with the tissue. But these are mainly as okay, processes or things that's going to happen to yes, okay, this sound wave here. Which cause that other end, yes, okay, it's going to yes, okay, be attenuated. So that's how yes, okay, these processes leads to or contribute to attenuation of the sound wave. Did you girls get that? Did you guys get that?
Yes.
Okay. So first, what is a reflection? Now you ladies may see yes, okay, a reflection every day. Every morning when you get up and okay, let's go to your restroom or bathroom or wherever you call it. Yes, okay, brush your hair, wash your face, brush your teeth. Because what is it that you do? Okay, yes, you'll be standing in front of the mirror. Now, what it actually appears to you is that, okay, that there's a person on the other side of the mirror that just looks exactly like you. Well, okay, there is no personal back on the other side of the mirror. That's mainly as okay, just you seeing yes, okay, your own reflection. Is that clear? Is that clear, girls?
Yes.
Good. Now, just a few things. We can mainly say it's okay. That's going to become important later on. Then we can say, okay, greater amount of energy that returns back. I mean, it's okay because of this term here, it's okay, back. That's why it's called a reflection. Or we can mean it's okay, because the return, or return here is that it's called a reflection. Okay. Or we can mean it says, okay, that okay, the greater amount of energy. What kind of energy in our case here is okay, would be sound. That is going to yes, okay, give us okay, yes, that's going to lead to yes, okay, working yes, okay. Later on, we'll see yes, okay, will be yes, okay, a brighter reflection. Because it carries yes, okay, a great amount of energy. Or this bright reflection is okay on your image is going to appear brighter. Yeah, okay, as on the other hand, we can say as okay, lesser amount of energy that is reflected. Or we can say as okay, return back. Which means okay, again, it's okay, or me, it's okay to reflect. Now actually it's okay, produce a darker reflection. And okay, it's on your image that is going to appear darker. Okay, so on your diagnostic imaging, you can mainly say as okay, because what is it that is going to be? It's mainly as okay going to be an image with different shades. Some shades are going to be bright. Some are going to be not so bright. Then you have, okay, some are going to be as okay dark and some not so dark. But it's mainly as okay going to be as okay from one side of the scale you have white, and on the other side of the scale you have black. And in between that is mainly as okay, there's going to be as okay different shades of gray that ranges between black and white. Clear? Okay. But for instance, okay, if you see as okay on your image something that appears bright white, what does that mean? That would mainly mean that okay, yes, this bright reflection here, or yes, okay, this bright shade on your image, mainly as okay is a reflection from a tissue that reflected a lot of the energy that it got hit with back to you. Or let's say it's okay, back to the transducer, which will appear as a bright shade on your image. And or the other way around. Okay, so when you go see something and okay, yes, it appears dark, not so dark, light, or yes, okay, very light. What makes it appear dark? Mainly because, okay, the amount of light energy that it has been hit with, it doesn't reflect it back. That's why you can make says, okay, the background here is okay, where my finger is, appears dark. Mainly because, okay, there's not much light produced in this area here. Whereas, okay, you go here. This is a great source of light that has been reflected back or being produced, and we see it as a great amount of light. Or it appears lighter. Yeah. This is thus as okay an example of okay as we can say as okay light energy. Okay, and sound is going to be the same. It will just become as okay a great amount of sound energy reflected back will appear as a bright shade on your image. Whereas, okay, if it's less amount of sound energy that's going to get reflected back, it will appear darker. And no sound energy reflected back, then it's going to, yes, okay, be pitch black. Did you girls get that? Okay. Now let's say, yes, okay, if you are wearing, let's say, yes, okay, white gloves and a black t-shirt, and you stand in front of the mirror. The reason that you see your black gloves that you are wearing as black is mainly as okay because it does not reflect any light back. That's what causes it. That it doesn't reflect any light back. Or we can say, okay, any light that it has been hit with is not bad reflected back. So you see that as black. Whereas, okay, something that, okay, appears white because, okay, you're wearing, okay, as new crispy white t-shirt. Appears white is mainly as, okay, because it reflects back all the light that is being hit with. Or you can mainly say, okay, when you add all the colors on the rainbow, they say the product of that is going to be white. Okay. Or mainly as, okay, due to this, because, okay, what happens to the light that, okay, hits your gloves, which are black? They will absorb that light. And that's why you don't see people who, yes, okay, walks in the desert wearing white, black clothes. Because, okay, the light that is, okay, that they are being hit with, which may come, yes, okay, from the sun. What is it that those black coats are going to do? Absorb that light energy, which then just becomes heat energy as well. And who in, yes, okay, who is walking around in a desert wants, yes, okay, be sweating to death? I don't think anybody will wish for that, right? So the reason that they wear light clothes, not light in weight, but light in color, if you are wandering around in the desert, is mainly because that's okay, it reflects back as, okay, all of the light that it's been hit with, and that keeps you cool. Yes, okay, somebody who looks at that person, yes, okay, will see him or her, yes, okay, wearing white clothes. Or the color of his clothing is going to appear white or lighter. Did that make sense? Mainly based on, yes, okay, the amount of energy that is being reflected back. So here is, okay, the same concept appears or applies, sorry. Okay. Any questions? So what is it that we're going to say as, okay, any sound wave that hits a certain surface, some of that energy that that sound wave carry, because we said that in chapter 2 that sound was a form of energy. So it's sound energy hitting a surface. Some of that energy that this sound wave had carried is going to return back. And what do we call that is going to return back? We call that a reflection. Clear? Oh, yes, okay, as far as, okay, because the audible sound, yes, okay, we may call that an echo. Clear? You say, how are you? And okay, yes, with a certain delay, yes, okay, you may hear your own voice coming back at you and say, how are you? Okay, which was mainly nothing but mainly as, okay, just an echo or a reflection of your own sound coming back to you. Okay, so here, and what causes that echo? Or what causes that reflection? Mainly as, okay, as we said earlier, that, okay, yes, if a sound produced by the transducer hits a boundary, some of the energy carried by this sound wave here is, okay, is going to, yes, okay, return back. And this return back, yes, okay, that's what we call a reflection. Clear? Where that is going to be, you can say it's, okay, strong reflection, or let's say it's okay, a weak reflection. That is mainly as okay going to be based on the nature of the tissue here. What that nature is, that's something that we'll talk about later on in this chapter here. Right. But we can mainly says, okay, any sound wave that okay as returns back will be referred to as a reflection. Returns back after what else? Okay, after hitting a tissue boundary. Did you girls get that?
Yes.
Now, ladies, that was just okay as the simple part, because now we go and see as okay. As far as reflection is concerned, we mainly as okay got two major types of reflections. One is going to be as okay what we will call a specular reflection. Clear? And the other one is going to be as okay what we will call is okay diffuse reflection. Okay. And as I've been saying, yes, okay, there are things which are going to, yes, okay, go under more than one name or one term. So this diffuse reflection here is okay, that is also as okay what we can call back scattering. Is that clear? Now, girls, what does it mean to have a diffuse reflection? A specular reflection? Or what we actually is okay, what need for a specular reflection is there is going to be as okay a sound wave that reflects after hitting yes okay a smooth boundary. So the main thing that we need for a specular reflection is that okay, yes, that the boundary is smooth. Is that clear? Now, if this is the case, you can say, okay, the relationship between yes, okay, your transducer and your boundary here. And we mainly says, okay, that here is okay, this is the sound wave. Let's choose this color here. That is being produced or sent out. You can mainly say that, okay, yes. Then, okay, this one here. And this is going to be, it's okay, your reflection. Coming back. Yeah. The same can also, yes, okay, is there going to be as okay a specular reflection? And we say as okay, we still have okay as a smooth surface. Let's say it's okay, a smooth tissue or a smooth boundary. But if in this case, we can say it's okay if our transducer is here. We can say it's okay, this will still be as okay the sound wave that hits it. But in this case, yes, okay, this will be as okay over reflection. Did you girls get that?
Yes.
Now again, yes, okay, the easiest way to explain what just happened here is okay as you and your mirror experiment. Just try that next time you walk into your restroom or it's okay standing in front of your dresser or something like that. Now goes, if you are standing right in front of the mirror, the reflection that comes back comes directly back to you. And that is pretty much okay, that's what we just had. Here. So the reason that you actually is okay, were able to, yes, okay, see yourself as a reflection was meaning it's okay because you were standing right in front of the mirror. Did that make sense? Now it's the same you, it is the same mirror. But let's say that, okay, as my mirror is here. And I'm standing somewhere over here. Or my mirror is here. And I'm standing somewhere over there. So, shoot. What will happen? Well, okay, a reflection is still going to be produced. But that is not going to come direct back to me. Or you may not see yourself in the mirror. Is that clear? As a matter of fact, you can mainly say, yes, okay, that, okay, yes, this is you standing here. The reflection of you is going to, yes, okay, end up here. Because you are not standing right in front of the mirror, right? Clear? But there may be somebody standing over here who will see your reflection in the mirror, but not his own reflection in the mirror or his or her own reflection in the mirror because that reflection comes back to you. Did that make sense? That's the second idea. So in both cases, okay, this is going to be as okay, or we can call it as okay, a specular reflection. And why were they specular reflections? Because, okay, your mirror in your household, a standard mirror in the household is going to be as okay, a smooth, straight surface. Did that make sense? or as your book may say, because, okay, for how long is it that is going to be straight of a surface? And the way that they say it is going to is, okay, be straight, a straight of surface which is bigger than a few wavelengths. Now, when it says, okay, a few wavelengths, what wavelengths? Wavelength of the sound. So the wavelength of your sound wave, or let's say it's okay, 1 millimeter. And it hits a surface which is, let's say, it's okay, straight for us, okay, 5 millimeters or so and so. Yeah, that could be as okay, that was going to produce a specular reflection. Because the surface is straight for a greater distance than a few wavelengths. Now you can always argue as okay, what's the number of few? It's going to be at least okay as more than just one. Clear? But if it goes direct, yes, okay, frontal like this, direct back. Whereas it comes like this, it goes just okay, yes, okay, reflect back like that. Yes, Shaq, you had a question, Maria.
So both of them, both example that you just told us is specular, correct?
Yes, yes.
And that's it. That's all. You answered my question.
Because what was it that you needed for a specular reflection? A smooth surface. Clear? In our mirror experiment, what is the surface? Your mirror, right? Clear? Did that make sense? And standard mirrors in standard households are going to just okay be straight surfaces or smooth surfaces, you want to put it that way. Okay. So yes, okay, the direction in which yes, okay, your sound wave is going to yes, okay, get reflected. Because okay, the direction of the reflection is going to yes, okay, not just going to be as okay based on okay as whether your surface is straight, but also as okay, and what direction is it that the sound wave hits the surface. Did you girls get that? So next time you stand in the mirror, it's okay, just do the side to side dance or something like that. Or do some line dancing and okay, you will see, yes, okay, all of a sudden, yes, okay, you disappear. You don't see your reflection. Somebody standing somewhere else may be able to see you in the mirror. And you may be able to see him or her as well. But he will not be able to see himself because he or she is standing as much off the mirror as you are. But he see you, you see him. Or she sees you, you see her. Did that make any sense? What made both of these here is okay, specular reflections is because the surface of the reflector, which is the mirror, oh yes, okay, here we can okay, the surface of the tissue is greater than a few wavelengths. Did that make sense? Okay, so pretty much okay, as structures in the body that produces, that'll be on your next question, right? Okay. When is it that we may okay come across as okay specular reflections? Is when you okay view or it's okay Or we can say it's okay that the sound wave is okay, hit structures such as the pericardium, CVT ladies, and the diaphragm. Because what is it that the diaphragm is? It's pretty smooth. Did that make sense? Anybody have any questions?
No.
No. Okay. Alexandra, are you there, my dear?
Yes, I'm here.
Okay. Sorry to play this game, but your last name is White, but the image looks pretty black.
Yeah, I don't know how to change it.
Your camera is off or what?
Yeah, it's off. I can turn
Okay,
it on.
but okay, now I don't know whether you guys could see us. Okay, Alexandra, let's see. Yeah, okay. But I don't see anything. Yeah, okay. Now. Okay, here we go. It worked now. So yes, okay, now it looks better, right? Okay. So I see something. Now, okay. Again, yes, okay, just remember, more energy reflects back, will appear brighter. Less energy reflects back, would be appearing darker. And you can say, okay, the more energy that is going to be reflected back, the more is it that the sound will attenuate because it loses more energy, which causes that there will be a greater decrease in its energy, which may mean that it will attenuate more. Did that make sense? Because when we say it's attenuate, yes, okay, we mean it's okay, compare, okay, what was the energy before it hits the surface? And when it passes on at the other side. So mainly because some energy is going to get reflected back. Less energy will continue on the other side, which will going to mean that it is attenuated. Now, girlies, the other kind of attenuation, reflection can be known as diffuse reflection. And or we can also call this one here back scattering. Clear? Now, if you look at the word back, all that means that's okay, account for. All be equal to yes, okay. No, sorry. The reflection. Mainly because it's okay, there is energy that is travels back towards yes, okay, where it came from. Clear? Where we can say is okay, the word diffuse is mainly as okay equivalent to as okay the scattering. Where okay as a common verb for diffuse or scattering can as okay also be. We can say it's okay to disperse. So the question mainly is okay, just arises, okay, arises. When is it that we will see is okay, diffuse reflection? Or what we call as okay, backscattering. So we can say as okay, we still yes, okay, have this transducer here. This transducer, yes, okay, it's still, we can say it's okay, may produce a sound wave. This sound wave here is now yes, okay, going to hit yes, okay, body surface. Which contrast to yes, okay, what we saw in okay as our specular reflection is not going to be smooth, but it's going to, yes, okay, we can say it's okay, it's either going to be, yes, okay, irregular as we see here. Is that clear? But what that actually is going to cause is that, okay, yes, what we have is what we will call as, okay, diffuse reflection, or yes, okay, backscattering. Okay. Now, it's mainly as okay going to be as okay a reflection mainly as okay because it's going to as okay traveling as okay away or in opposite direction of okay as this initial sound wave here. Okay, so it's going to as okay. That's what called as okay makes it okay as a reflection or back. It's going to travel in this direction here. Okay, but we call it diffuse. Or scattering. Because it's going to go like this. Contra to yes, okay, what we had in our regular or specular. And okay, yes. This, and then we're going to see it's okay, this with our reflection back. Did that make sense? There, okay, here because there's okay, our surface was smooth. We say either it was smooth or greater than a few wavelengths. What did we mean by wavelengths? The size of the wave from beginning to end. Did you girls get that? Did you girls get that?
Yes.
And that mainly is okay, also is okay, can bring us because okay, I was going to be as okay an equivalent to this explanation here for as okay backscattering or diffuse reflections. is mainly as okay is going to be as okay that because it's okay the size of the surface. Where surface can also as okay be referred to as the boundary. V as okay may also as okay referred to as the tissue. Or we can even as okay go as much and say as okay referred to as the reflector. Because what is it that it's going to do? That's going to be the substance that produces the reflection. Or I mean, you can say that the size of the surface, a boundary or tissue, a reflector here is lesser than the wavelength. And again, yes, okay, what did we mean by the wavelength? Size of the wave of one cycle. Okay. So goes examples, yes, okay, where we see yes, okay, diffuse reflection or back scattering is going to be as okay in case of red blood cells. If this cell here is okay, tissue here was okay as red blood cells. You most likely as okay are going to as okay experience diffuse reflection or backscattering. Here, another common example is okay where we as okay see diffuse reflection or backscattering is going to be as okay in the case of an alveoli. Mainly because okay, both these fellows here is okay as far as the size of them are concerned are microscopic.
What was that second one?
Alveoli. Now girls, let's just go back to yes, okay, to our mirror experience. Now, some of you may have yes, okay, those kind of mirrors where you look into them and okay, something appears bigger than they are. Or you may yes, okay, look into a mirror and okay, the object that you're looking at appears smaller than you are, than it are. That is mainly as okay due to yes, okay, diffuse reflection. Or have any of you ever gone to yes, okay, playland where they have those fun houses? And you walk through yes, okay, a series of mirrors. And in one mirror, yes, okay, you look at yourself and okay, as your head is this big and your body is this small. Then you walk, that's okay, by another mirror and okay, as you go like this. But nowadays, that's okay, you don't really have to, yes, okay, go to, yes, okay, play now. So they have, yes, okay, all these crazy filters on Snapchat and WhatsApp and TikTok and whatever you call all that crap. Okay. But if you want to, yes, okay, you can disfigure yourself. Okay. But what is it those filters are? Mainly, yes, okay, you can say, okay, here, uneven, irregular, yes, okay, surfaces of a reflector. Or they produce an image just like that. Is that clear? So yes, okay, 2 reasons why you may have backscattering. Or what we call diffuse reflection is either because, yes, okay, the surface of the tissue that you are scanning is irregular. Or yes, okay, if it is smaller than the wavelength. Did you girls get that?
Sorry, what was the second reason you said? You said surface of tissue is irregular or,
That's one reason.
and what was the other
It's
one?
irregular, right? Okay.
Yeah.
Which is just compared to, yes, okay, when we talk to smooth, that's okay. Specular reflection where the surface was smooth. Clear. The other we said was that the surface of the tissue or the size of the tissue that you are scanning is smaller or is lesser than the wavelength.
Gotcha, thank you.
Yep. Okay. So that's mainly going to cause, okay, as sound wave hits, sound wave hits, yep. Okay. And another name for your diffuse reflection is back scattering. That the reflection part is just okay, coming back. Scattering is not okay, tung tung. All right, tung. Okay. That means okay, means to scatter out or disperse. Did you girls get that? Okay. But what it actually is okay, it does to the amount of energy that proceeds, is going to reduce that. Okay. So as says, okay, sound wave hits tissue after tissue after tissue after tissue after tissue after tissue. What happens? Certain amount is going to just okay, get reflected back. That's what you actually just okay want to happen so that you can produce an image. Or at least says okay, produce as okay, get reflections, which will give you, well, okay, what kind of tissues or what is the nature of the tissues that the sound wave pass through. Yes, okay, as I'm scanning this area here. And that's going to produce a picture that you will see. Picture is probably as okay. Too ambitious of a statement, but yes, okay, you will see something. Okay, and then it's going to be as okay, what is this? What is this? Okay. Did you girls get that? Did you girls get that? So I'm looking at, okay, as some girls who have some homework to do. Go and look in the mirror from different angles, okay? Don't say anything, just go and look at the mirror from different angles. Ask somebody to stand somewhere else or put an item and say, okay, can I see that in the mirror? You have to be at an equally off angle to the mirror to be able to see that object or substance or person as well. Let's take a fish. Good mud, but should we check scattering as well? Okay. Somebody just shook their head. Is that because it is chilly or because they got enough? Okay, ladies, we already talked scattering. Yes. Indirectly we did. When we say back scattering. Here we just take off the back part and say scattering. So what is scattering? Dispersion, right? So we can say, yes, okay, what happens? And here it's okay, it's irrespective of whether it's okay that surface is smaller or bigger, etc., etc. We can mean it says, okay, transducer. We can have, okay, a surface. Sound wave hits. Right. We may, yes, okay, in this case, yes, okay, still have, okay, as good reflection. But at the same time, yes, okay, there were also, yes, okay, or there may be scattering. Where we can say, yes, okay, this here, or these scatterings here, is okay, that could just have been backscattering, or what we call is, okay, the diffuse reflection. Whereas, okay, you in this here is, okay, dispersion or scattering of energy. Yes, okay, together with this, all will be called scattering. Did you girls get that? So we can mainly say, okay, what scattering mainly is, okay, is where there is dispersion of the energy that is spread out. Okay. If some of you, yes, okay, it still doesn't mean what scattering is. Well, girls, I'm not going to pay for this experiment here. But I will verbally, yes, okay, demonstrate it. Because what you need to do for this experiment here is, okay, you take a plate and you smash it on the floor. What's going to happen? It will break, right? The plate will break. But then you will say that, okay, that's okay, the plate broke or the cup broke or whatever. It's okay, piece of, okay, yes, crockery that you want to take your, yes, okay, frustration out of. Okay. Well, what's going to happen to the pieces of that plate, cup, glass? They're going to scatter. What do you mean by that? Now, okay, I dropped the plate right here, or the cup or glass or whatever, but I find pieces of it over there. Some pieces over there. Why? Because it's scattered. Did that make sense? They scatter, yes, okay, they dispersed. Now, girls, earlier when we talked of vectors determining attenuation. You remember that one? Which were, yes, okay, wavelength and frequency, not wavelength, sorry, path length and frequency. And I said, well, okay, it's common sense. Somebody standing nearby is, okay, will be able to hear the sound produced, or the words being said or whatsoever. Somebody is, okay, at a far distance will having a hard time because at that distance, the sound would have attenuated. Right? Then we said frequency. I say, oh, I don't really have much of an explanation for that. You just gotta memorize that one. Okay. But you can say as okay, one of the processes in which is okay, mainly as okay, have more attenuation as a result of high frequencies due to scattering. So we based on that, ladies, mainly can say as okay. Okay, let me just do it this way. Say that okay, yes. Your frequency mainly as okay is going to be as okay, we can say as okay directly proportional to scattering. That mainly as okay just will make it, we can say as okay, also as okay directly proportional to your attenuation. So we can make as okay, it's primarily as okay due to as okay the sound undergoing as okay at scattering, that okay, yes, this higher frequency sound here as okay may have greater attenuation because a high frequency sound causes more attenuation scattering. And likewise vice versa. Did you girls get that? Did you girls get that?
Yes.
So we can say as okay, at least for this example, or at least for this instance here, had it not been for the sound wave undergoing scattering, frequency would not have been a determining factor of attenuation. Did that make sense? Did that make sense, girls? Okay. Now, with that said, and for now, just remember, most likely as okay tomorrow if you get just okay. When we get that far. Well, okay, it may help you just okay be able to remember what I will ask you girls to remember, or you can make some sense out of it. Because okay, there are some tissues in the body that we can say, okay, although yes, okay, was the same frequency. Or is okay, we can say it's okay, a transducer, and just okay, same frequency. But mainly as okay, based on the nature of the tissues. Some tissues may as okay have, we can say as okay, more scattering. Which mainly as okay, then just cause them to as okay have a greater attenuation. Okay, and out of the many tissues or yes, okay, structures in the body, yes, okay, which has, or which actually is okay, causes as okay, we can say okay, a great amount of scattering of the sound wave that is being hit with, that tissue is going to be as okay, the lung. Okay. So that is made as okay, YV as okay, also can say as okay that the lung that's going to as okay, B as okay, yeah. Very, very highly attenuating structure. That may sound crazy, but this scattering here as okay is mainly as okay the reason why. Is that clear? Okay. So yes, okay, although lung is okay as a loose spongy tissue, it's not thick and dense as a bone, for instance, or as a muscle and so. But it is going to, yes, okay, be causing a lot of attenuation to the sound. And one of the major factors that causes, yes, okay, that increased attenuation is that the lung as per nature causes a lot of scattering of the energy. Which means it's okay, that the energy hits, gets dispersed. That makes sense. But as you can see, it's okay, as far as okay, as factors that may be in our hand, we can say it's okay. If you want to cause less scattering of the tissue, let's say it's okay to enable it to travel through the lung. We then would have to use as okay a low frequency transducer. Because that lower frequency will reduce the scattering, which will reduce the attenuation. Or we can relate that to, yes, okay, that's a segment here. Or we can relate that to, yes, okay, dropping the plate or cup or glass. You says, okay, just slipped out of your hand and it fell. It may just break into 2 pieces or 3 pieces, which are going to be right there. Right, okay, we say, okay, at least I didn't throw it on the floor. I just dropped it. There, okay, as that high frequency, that going like that. And what happens then? Or okay, yes, okay, use the whole swing of an arm. All your biceps, triceps, and all that to throw that glass or plate or whatsoever, a piece of crockery on you on the floor. And what's going to happen next? The pieces are going to be scattered all over. Yes, Jack, you had a question, my dear.
I forgot it. That's
You
why I was gonna
forgot
try
it?
to get a piece of paper. Yeah.
Okay.
Sorry.
Okay, I hope I answered it unknowingly. Okay. Did that make sense? Clear? So you can say it's okay, less frequency with same tissue, less scattering, less attenuation. So it's primary, yes, okay, it is due to your scattering that frequency of the sound is a determining factor of attenuation. Did you girls get that?
I remembered now.
Hmm.
So when someone has the ultrasound of the lung, They have to basically scan them with a low frequency transducer.
How many?
Do they, when someone has a ultrasound of the lung,
Mhm.
so the sonographer has to scan them with a low frequency transducer?
Well, not necessarily, but you may just have to know the factor that as sound passes through lung, meaning because lung, as per nature, is a tissue that causes great degree of scattering. It's going to lead to a great amount of attenuation. Yeah. So the main relationship that is important here is what is the relationship between, you can say reflection, scattering and frequency. Clear? Okay, so higher frequency, more scattering. Lower frequency, less scattering, which mainly makes as frequency and scattering directly proportional to one another. Clear? But then you can also there are some tissues, and as an example would be the lung, which by nature is a highly attenuating structure. Why? Because it causes more scattering. Or we can say the main process that the sound wave undergoes that causes a great degree of attenuation in the lung is scattering. So you can put it this way that as if you scan the lung with a lower frequency transducer, there's going to be less scattering. Less scattering will lead to less attenuation. Okay. But then your less frequency transducers, they have their own disadvantages. So it means going to be advantage versus disadvantage. Okay, which disadvantage is it that I still kind of clear with and still get my results? Or what is, which means what is that you want to achieve by the scanning? Or what are your goals? Does those goals allow you to use a high frequency transducer? Or have you go on the low frequency? Because everything that has a disadvantage also have a disadvantage. Did you girls get that? Okay, girls, we will take up, Rayleigh scattering tomorrow. This is just as a subtype of scattering, okay? Okay. Any last words of wisdom? Or any question that just came to your mouth or minds?
What day are we having off this week? You said that you'd let us know on Monday.
Sorry, 28. There it goes. Let me just see. Yeah, sorry. That's going to be 28, which is on Wednesday. Okay, so you will not have class on Wednesday. And then that is it. I will not be checking off. Anything else besides that's okay? Nope. Okay, so tomorrow's going to be okay, a bit of a hell of a day. Because we need to talk on reflection, scatter, release scattering, absorption. Oh, that's a quick one. It's the attenuation coefficient. Okay, yes, that's when math comes in. Attenuation in different tissues and half layer thickness. I mean, it's okay, just incidence, transmission, and reflection. Okay, so it's not that much material. It's okay, make sure that you read on it. Okay. Anything else goes? Yep. Okay, girlies, then I guess I will see you girls tomorrow at 9 o'clock.
Okay, thank you.
Thank you. Bye.
You're welcome. Yeah.
Thank you.
You're welcome. Yeah. Bye-bye.